Let me take you from the stars down to Earth, from the telescope to the microscope. And these are two extremes, but you will find my talk comprehensive, I hope. So there were three surprising discoveries in the mid-80s that more or less shook the world in a way, and they brought 3 Nobel Prizes, and the last one is here. Although the first discovery, chronologically, was that of quasicrystals, as you see here, and the names on that are, my name is Ilan Blech, Denis Gratias, and John Kahn. I'll tell you about them later on. Then came Fullerene by Kroto and his colleagues in 1985, and in 1986, high-temperature superconductivity. Now, there was superconductivity before, since the early days of the century, and but the high temperature was not there, so this was quite surprising. Fullerenes were also a nice way to pack carbon atoms, but the quasiperiodic crystals were quite amazing because they were, as you were just told, against the laws of crystallography. And this is our subject today. So let us, in order for you to understand what I'm talking about, let's bring a few basic concepts. And the first one is order, then we'll talk about periodicity, and then we'll talk about rotational symmetry. So imagine that we have here a picture of atoms which are arranged in a periodic way, and look here, you see that there is order, and also there is periodicity. And if I would ask you what will happen next, up here you will tell me there should be an atom here and an atom here, so you will clearly understand the order. And this periodicity can come up in each and every direction that you look at, like so. There is periodicity everywhere. Also, you can rotate the crystal, and you can rotate it in such a way that it repeats itself. So, for instance, this model can be rotated 4 times, and then it comes back to where it was before. But if I rotate it only 1/4 of a turn, like 90 degrees, it will look the same. And in order for you to see that it looks the same, let's add a little handle here, and then rotate it 90 degrees and 90 degrees more. And finally, it repeats itself. So this type of crystal will have a 4-fold rotational symmetry. Okay, so this is a periodic, ordered crystal that have a 4-fold rotational symmetry. And rotational symmetries in crystals can be repeated in several ways. Then there is 2-fold rotational symmetry, 3-fold rotational symmetry, 4-fold, and 6-fold. 5-fold can be done only in a point group. This flower can be rotated. Okay, so this is about rotational symmetry. Now, let's talk a little bit about crystallography. The science of crystallography really started in 1912 by the famous experiment by a German scientist named von Laue. And he showed in one amazing experiment that both X-rays have a wavy nature and atoms in crystals are ordered. And his crystal was not only ordered, he was also periodic. And now you know what periodicity is. And all the crystals that were studied during the 70 years between 1912 and 1982 were ordered and periodic. And so, based on these observations, a definition of a crystal was evolved. And it was the same definition, although different books used different words. And I will give you just two examples. A crystal may be defined as a solid composed of atoms arranged in a pattern periodic in 3 dimensions. This is in one book. Another book will say atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. It's exactly the same definition. Periodicity equals order. This is it. And this was the definition of a crystal. And then there were books. These were the books that we have studied. This is a book on physics by Kittel. And what it says here you cannot see, but now you can see. And the book says the following. We can make a crystal for molecules which individually have 5-fold rotation axis, but we should not expect the lattice itself to have 5-fold rotational axis. So this was the wisdom, and the science of crystallography was a mature science. Nobody expected anything new to be discovered. Nobody looked for anything new. And whenever somebody discovered a new crystal, they could, by X-rays and microscopy, decipher the structure. And there were drawers. For instance, you discovered a crystal whose symmetry is DO19. So there was a drawer for DO19. Welcome, new crystal, added to the hundreds of crystals that are already there. This was the science. And then let's look here at atoms in a crystal. This is a high-resolution picture of atoms in diamond that I took years ago. And what you see here, these are the actual atoms, and you see the order, and you see the periodicity. Everything is nice and really, really easily understood. So the order in carbon atoms in diamond is periodic, and the allowed rotational symmetries are 1, 2, 3, 4, and 6. 5-fold rotational symmetry, as well as any other symmetry beyond 6, is forbidden in periodic structures. And now let's look at the diffraction pattern from a periodic crystal. This now is a diffraction pattern, electron diffraction pattern. These are not the atoms. This is the reciprocal space of the real space. This is the space of the diffraction pattern. And what you see here is that the same rules apply. There is periodicity of the diffraction peak in the reciprocal space. The rotational symmetries that are allowed are again 1, 2, 3, 4, 6. No 5-fold, nothing beyond 6. Nice and clear. And then came up a new definition of a crystal. And this definition came in 1992. And look at this beautiful definition. It says the following. By crystal, we mean any solid having an essentially discrete diffraction diagram. And by aperiodic crystal, we mean any crystal in which 3-dimensional lattice periodicity can be considered to be absent. Why is this definition so nice? Because it is humble. Because it is open. It doesn't say a crystal is. It says by crystal we mean. We are becoming humble. Imagine that, the science of crystallography. And because we only mean any solid having an essentially discrete diffraction pattern, and so on and so forth. A humble scientist is a good scientist, and the field of crystallography opened. So what happened? What happened in 1992 that we had to change the definition of a crystal? So in 1982 was the 70th birth of crystallography, and this was the year the quasi-periodic crystals were discovered. This is a picture of my logbook from the electron microscopy. It was not meant to be seen by anybody but me, but hey, fate did it, and now this became a famous logbook. What you have here is everything I needed in order to understand what I did days before. So this page says the following. First of all, the date is April 8, 1982. The alloy I was studying is aluminum 25 weight% manganese. SAD means selected area diffraction in the electron microscope, and so on and so forth. So I took a few pictures. pictures. And then plate number 1724, 36,000 times magnification, and I see crystals which are pitch black. Pitch black can mean two things. Either the specimen is so bad, that it is so thick that the electrons do not go through, or that the crystal diffracts electrons so intensely that the transmitted beam is left with very low intensity, which was the case. And I was telling myself, hey, that's quite an interesting crystal. Let's look at the diffraction pattern. And I look at the diffraction pattern, and I say, tenfold, and this is the diffraction pattern you saw before, and you will see it again. And then the question was, okay, I will go through whatever I did here because it seems to be a little bit important. Then I said, okay, tenfold. Later on, it turned out to be fivefold, but I could not find out by this method of diffraction that it was really fivefold. It has to be done by another experiment, which we did later on. And I said, okay, this must be twinned crystal. That means five crystals, which have a special boundary between them, like that. If these are atomic rods, they have a special boundary. And if you have five of them, then you have five superimposed diffraction patterns that will give you this diffraction pattern that I have seen. And I said, okay, let's find these twins. Let me just find them and forget it. So I started to perform a series of experiments. These are called dark field experiments in the transmission electron microscope, which were designed to find those twins. I didn't find them. So I performed another experiment called microdiffraction. See, all these three pictures are microdiffraction. Mu diff means microdiffraction. Microdiffraction means that you converge your electron beam onto a spot, and from that very little tiny spot, you take the diffraction pattern. And if there is a tiny, very small twin, just one, then I will get an ordered periodic diffraction pattern, which will show me that there are twins, and there's nothing else there. No twins were found. So by now I knew that I have something very special. I didn't know what it was. But I knew from day one that there were no twins. And this becomes important later on because the opposition said up until 1994 that these are twinned in crystals, and I knew from day one it was not. Okay. So let's see, what is the first view? This is the picture that I saw. And look at these grains, which are very, very dark, pitch black. These are not, these are. And I said, that's quite interesting. And I took the diffraction pattern, and this is the original. This is the first picture. This is the original picture, diffraction pattern with tenfold rotation symmetry. And I sit at the microscope, you know, an electron microscope, quite similar to a telescope. You sit alone in the dark, and your eyes are glued to a screen or to binoculars, and you observe the universe, large and small. And so I see the diffraction pattern, and it looks very strange to me. And I start to count the point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, there's no such animal. And I count them again the other way, and it didn't change. So this is why I wrote tenfold. Unbelievable. Okay. So the other thing about this diffraction pattern is the fact that if you look at the periodicity, there is none. For instance, if you measure the distance of this point to this point and multiply it by any integer, let's say 2, this distance, you arrive here and there is no spot here. So there is no periodicity in this order. And then it turns out, you cannot measure it of course, but it turned out that the ratio of this to the center to this to the center is the golden mean, or the Fibonacci number, tau, or phi, which is an irrational number. Welcome irrational numbers to the field of crystallography. Another problem. Okay. So, by the way, this is the Fibonacci number, 1 plus root 5 divided by 2, 1.6, and endless list of numbers. Now, the fivefold rotation symmetry was not the only one. There were other symmetry depending how you tilt the crystal. So from this point it says 5-fold, this point 3-fold, this point 2-fold. So I played with it and turned the crystal each and every way. And this was the list of patterns that arrived. So we have 5-2-5 and 5-3-2-3. And this is the base. These are the basic diffraction patterns that you find in that crystal. Now, why did I think that there were twins? Because years before, I have observed this crystal. I never published it because it was so mundane. Okay, it's so simple. This is in the aluminum iron system. And as you see, this is a single crystal, and this is a single crystal. In between them, you have a twin boundary, and another twin boundary, and another. So we have 10 single crystals. And if you take a diffraction pattern from all of them together, then you get a pseudo 5-fold rotational symmetry that looks like that. This I had years before. So this is why I was looking for the twins. And so you see that if you count them, you see 10 points. But really, this is superimposed images. To see that, you can do the following. Okay, here is one. Periodic, no problem. And if you have 5 of them, then you get what you got. Okay, so this was the basic understanding before, and this is why I knew that we have something new here. Okay. And then these dark field experiments, let's just briefly go through them. Okay, so what you have here is the following. In dark field experiments in electron microscope, what you do is you take a picture using only one diffraction spot. And when I did that, this was the image. When I use this diffraction spot, this was the image. And as you can see, you don't see, this is one crystal, and it is not divided into any sub-crystals. So there were no twins here. That was clear. And then I did the microdiffraction experiments, and the same thing. And the size of the beam was 40 nanometers, which is 400 angstrom, quite small. So if there were twins there, they must be much smaller than 40 nanometers. And then, finally, this picture arrived from colleagues in France. I did do that. This is high-resolution microscopy. The first high-resolution microscopy results from quasiperiodic material. And they did a wonderful experiment. And this experiment is the following. You see, this is the diffraction pattern from this crystal. But what you can do is take a slide with this crystal and make an optical diffraction. Just put the slide here, put a laser beam here, shine through, and what you get is this diffraction pattern. This is optical diffraction. So the mathematicians among you will say, well, what's the big deal? You do a Fourier transform from this to this. You do a Fourier transform back to this. It should be the same thing, of course. But then what you can do as an experiment is the following. You can limit your field and bring it down to minimum, and still this diffraction doesn't change. It will fade away for lack of information, but it doesn't change. Okay, so it was clear by now that these are really special crystal and really something new. And this is a more modern picture of quasiperiodic material, and you can see some building blocks here. You see all these tenfold pattern which never repeats themselves in a periodic way. What happened next was the following. I came back to the Technion in late 1983 after 2 years of sabbatical at NBS, where I made a discovery at the invitation of John Kahn, who was an eminent scientist at that institute. And there I met Ilan Blech. Ilan Blech contributed to the field two very important things. He helped decipher the icosahedral structure, and he proposed a model that explained how these diffraction patterns could have evolved. And then, when he did that, we took both of our results, put them together in a paper, Shechtman Blech, and send it for publication in one of the journals of the physicists, and it was rejected very, very quickly on the grounds that it will not interest the community of physicists. Okay, and they suggested, why don't you send it to a metallurgical journal, which I did. So immediately, you know, those days, everything was paper, stamps, envelopes, remember? So I sent it to another journal, a metallurgical journal, Metallurgical Transaction. They accepted it, and it was published. But it was published months later, more than half a year later. In the meantime, I showed my results to John Kahn. John Kahn was very enthusiastic about our findings and results, and he proposed to write a different paper, much shorter, much more concise. And to do that, he invited Denis Gratias, an eminent mathematical crystallographer from France, and the four of us published a much shorter paper which had all our names, Shechtman, Blech, Gratias, and John Kahn. And this paper was published in November of 1984. And this paper really opened the field of quasiperiodic materials. What happened next was the following. Shortly after our publication, there came another publication with another model by Paul Steinhardt and Dov Levin, who suggested a mathematical model of quasiperiodicity in these structures. Their work was based on Penrose tiles, named after Roger Penrose, a British mathematician, and based on experiments by another British mathematician, Alan Mackay, who showed that you can take Penrose tiles, and I will show you Penrose tiles in a minute. You can take these tiles, shine a laser beam through, and create a five-fold rotational symmetry diffraction pattern similar to what I have observed. So they, Paul Steinhardt and Dov Levin, contributed not only the name quasicrystals to the field of quasiperiodic materials, but also contributed this model, which has been accepted as the mathematical model of quasiperiodic materials. Let's talk a little bit about icosahedral symmetry, because the first phase that I have discovered had icosahedral symmetry. What you see on the board is an icosahedron, and an icosahedron is the basic structure of many quasiperiodic crystals which have this symmetry. And an icosahedron has 6 five-fold X's. Now, if you look from this point to the center, you'll have five-fold rotation symmetry. It has 10 three-fold X's. If you look straight here, you see a three-fold rotation symmetry. And if you look from this point to the center, or from this point to the center, you see a two-fold rotation symmetry, and we have 15 of them in an icosahedron. This explains exactly the structure of the icosahedral phase, and this is why the name was given to it. And the main rotation symmetry of the icosahedron are similar to those of football. Oops. No. Oh, no. I don't know how to bring this back. Okay. The years 1984 to 1987 were the years of rejection. Before, there was local rejection. And the reaction varied from what John Kahn told me in the very early days. He said, Danny, this alloy is telling us something, and I challenge you to find out what it is. This was good reaction. Bad reaction was that of my group leader, who expelled me from the group because I was a shame to the group. Okay, it didn't make much difference. I stayed in the same office, and I worked in the same laboratory, but I reported to another secretary. But these were the reactions. Okay, and for a while, this is how I felt. But then, when Ilan Blech joined, and then John Kahn and Denis Garza joined, I was not alone anymore. And from there on, we were fighting a winning battle, and it was clear that we are going to win this battle because we knew we were right, based on experimental evidence that I have produced before, and based on the models of Blech, Paul Steinhardt, and Dov Levin. So it was clear that we are going to win this battle. Now, what happened in 1987? 1987 was a crucial year for the acceptance of the science, because then we had 5 minutes. Then we had the first Xray results. And the International Union of Crystallography wanted Xray results because this was the tool, the science, the name of the science was Xray crystallography. They wanted Xray results. Colleagues of mine from France and from Japan sent me Xray results. Why didn't we have them before? Because we did not have large enough crystals. By now, these guys developed large enough crystals, and they could take single crystal diffraction pattern by X-rays. And when I presented these results in Perth, Australia, in 1987, the community said, okay, Danny, now you're talking. They established a committee to redefine crystal, and you have seen the definition before. Linus Pauling was the last opponent, a very strong one, a single person, but the American Chemical Society was behind him, and so he had battalions of scientists behind him, and he was standing on stages saying, Danny Shechtman is talking nonsense, and there are no quasi-crystal, just quasi-scientists. Well, that's what he said. But then he died in 1994, and with him there was no more opposition to quasiperiodic materials. Okay, because of, in the sake of time, we'll go very quickly. These are the results of the X-ray diffraction patterns, beautiful Laue diffraction patterns that I have shown in Australia. Let's say a word about Penrose tiles. These are Penrose tiles, Roger Penrose. They are composed of a thick rhombus and a thin rhombus, and these two rhombi can pave the two-dimensional space in a way that covers the space with no gaps. And what Ellen Mackay showed is that when you take a diffraction pattern from this, you get the diffraction pattern, optical diffraction pattern that I have found in this material. And this is a three-dimensional view of a quasiperiodic material, and this is based on the magnesium-zinc cerium system, and it was grown in my laboratory, and we have been doing this many times. Okay, and here are some other examples. So, while as before order was a synonym to periodicity, now we had a new definition, and order could be either periodic or quasiperiodic. The field has opened. Okay, so let me answer you two questions you did not ask. Number one, why quasicrystals were never discovered before 1982? Now bear in mind that hundreds of thousands of crystals were studied during these 70 years, from 1912 to 1982. Nobody saw any quasiperiodic material? Why so? Well, maybe they are very rare. No? Well, we'll see. Maybe they are not stable. You hold them, they disintegrate. Maybe they're very difficult to make. Well, they're not rare at all. In fact, there are hundreds of them. These are some of the quasiperiodic materials based on aluminum alone. And we have hundreds of them. They are abundant all over the periodic table. Okay, are they not stable? Well, many are. But what does it mean? It means that you have to heat them up to 300 degrees, 400 degrees C for them to transform. But when you hold them in your hand, when you have them in the microscope, they are fairly stable, no problem. People could have found them. And here are some examples of stable quasiperiodic material. And then Maybe they are difficult to make. Oh, not at all. You can make it in any way you make any material, by casting, by rapid solidification, single crystal growth, electrodeposition, CVD. Sorry, all these terms may not mean much to you, but surely they mean much to the engineers. So easy, it's easy to make. And these materials are cheap. They are not, we talk about aluminum and manganese and iron and chromium, and abundant, cheap, easy to make. So this is not the right answer. So why, this is the second question, why were they not discovered before? Let me try to answer this. This is my answer. And many people may have a different answer. First of all, quasiperiodic materials had to be discovered by transmission electron microscopy. This is a victory for transmission electron microscopy. You could not have discovered them by X-rays because the crystals were too small. And you could not get a single crystal diffraction pattern from a crystal that was, by X-rays, from crystals the size of which is 2 microns. You have to have something that you can hold in your hand. Something that you can feel between your fingers in order to see, to put it on something and take an X-ray diffraction pattern. And these were available only 3 years later. So TM was the tool, must have been the tool of discovery. Then you need to be a professional. And you have to have tenacity. It means that you have to trust what you are seeing. Now, here's an example. I was told by a group in Europe that somebody saw these diffraction patterns before me. And he filed them. End of story. He didn't pursue to continue to try to understand what he saw. And you have to stick to it against opposition. And the opposition was there. And you have to believe in yourself as a scientist. And this is the message that I try to convey to young people. Become an expert in something. Become an expert now, when you're in high school. You can start now. And it will carry you a long way into the future. And you have to have courage. Now, for me, it was natural. I knew that I was right, and so. But other people tell me, somebody say I would file my findings, and because I was early in my academic career, so you had to have some courage. Okay, thank you very much for your attention.